The Rosalind Franklin rover has a ride to Mars. This week on Planetary Radio. I'm Sarah El-Ahmed of the Planetary Society, with more of the human adventure across our solar system and beyond. This week I'm joined by Jorge Vago, ExoMars project scientist at the European Space Agency. We'll talk about the Rosalind Franklin rover's journey to the launch pad, the science that it's going to do when it actually gets to Mars, and what's coming up next in the search for life beyond Earth. Then stick around for What's Up with our chief scientist, Bruce Betts, where we talk about the ExoMars Trace Gas Orbiter that's been waiting to send the rover's data back to Earth. If you love Planetary Radio and want to stay informed about the latest space discoveries, make sure you hit that subscribe button on your favorite podcasting platform. By subscribing, you'll never miss an episode filled with new and awe-inspiring ways to know the cosmos and our place within it. The Rosalind Franklin rover has had one of the longest roads to the launch pad of almost any mission in European Space Agency history. It's part of the ExoMars program, whose first mission, the Trace Gas Orbiter, launched back in 2016 and is still operating at Mars today. Rosalind Franklin, sometimes called the ExoMars rover, is the second and final piece of the program. First proposed back in 2001, it's weathered partnership changes, redesigns, and no shortage of setbacks along the way. Through all of that, the science at the heart of this mission has stayed remarkably consistent. Rosalind Franklin will be the first Mars rover to combine mobility with the ability to drill 2 meters beneath the surface. That means that it can reach material that's been shielded from radiation for billions of years. That could teach us so much about Mars's past habitability. The rover's set to land in Oxyaplanum, an ancient, clay-rich region that some scientists hypothesize may have once sat along the coast of a vast Martian ocean. My guest today has been with the mission since the very beginning. Dr. Jorge Vago is the ExoMars project scientist at the European Space Agency's European Space Research and Technology Center in the Netherlands. And now, after more than 2 decades, the mission finally has a rocket and some launch windows. Here's my conversation with Jorge Vago. Hey, Jorge, thanks for joining me.
Thank you so much. It's great to be here.
And wonderful to have another Mars rover to look forward to. I've been following this mission for so many years, and seeing the developments that have been happening over the last few months has been really exciting.
Indeed. We've had a rather longish development for this mission, longer than most.
It's true. And you've been kind of described as one of ExoMars's founding generation. You've been working on this for so long, and now Rosalind Franklin finally has a rocket and a potential launch window. So for someone who's been in the room from the very start, what does that mean to you to finally have a ride to Mars?
Oh, it's amazing. It's a mixture of elation and relief, I would say, because we started thinking about this mission in 2002. If you think, we had the announcement of opportunity for instruments in 2003. That was even before Curiosity did their own. But we've had so many ups and downs.
It's been a long road to get here, but it sounds like we're finally on a good path. We've got a good idea of roughly when it's going to launch. Do you want to give anybody an update on when that launch window actually is?
Actually, we have 2. So the first launch window is in September, the end of September 2028. But we actually like the second one a lot better, which opens in December 2028. And the reason why we like it better is because even though we launch 3 months later, we arrive 4 months earlier. And on top of that, the landing is in the morning, which means that the rover, which uses solar panels, has the rest of the day to top up the batteries.
What's going to dictate whether or not you go with that first or second launch window?
I think schedule. We are at the moment trying to target the first launch window, because if something happens, then we have the second as a backup. But we don't have a backup for the second launch window. So the project team thinks that it's the prudent thing to do to try to make the first launch window. And then when we're almost there, we can always switch to the second one. Whereas going directly for the second one, it's okay, we could do it, but you're hedging your bets.
Yeah. And you never know what's going to happen down there. We've seen with some recent missions in the last few years what happens when hurricanes change timelines for missions, or, even just a delay because of a lightning storm or something. So it's always good to have multiple options for sure. But before we get deeper into the actual mission itself, I want to talk a little bit about its namesake. Who was Rosalind Franklin, and why was she the right person to name this rover after?
So Rosalind Franklin was a British scientist who had a pivotal role in the discovery of the structure of what would turn out to be the DNA molecule. She died from cancer before she could take part in the Nobel Prize that was given to Watson and Crick. So it's a bit of a sad story. Also, she wasn't exactly treated right within the project team that was doing the research. So I think it's deserving, even if it comes after all this year, of this scientific justice has to be done to her contribution and to her name.
You've described ExoMars as the first mission to investigate Mars in this third dimension, depth. How deep can ExoMars' Rosalind Franklin rover actually drill beneath the Martian surface?
Before I answer that question, I need to put into context what we have done so far. So the depth record on Mars still lies with the Viking landers that touched down in 1976, and it's about 17 centimeters. And the reason why going deep is important is because Mars's atmosphere is incredibly tenuous. It has a pressure that Earth's atmosphere has at 30 kilometers altitude. So way higher than even the Concorde flew. So there is an atmosphere, but there's not much of it. And the result of that is that ionizing radiation, so cosmic radiation or solar proton events, penetrate the atmosphere and even penetrate into the ground. So if you're looking for traces of life, it turns out that this radiation over the years, over millions of years, is very slowly destroying what you're trying to study. So we said, if we're interested in targeting the biosignatures, the relics of a possible life that may have existed on Mars 4 billion years ago, when it looked more like Earth, it is clear that to access biosignatures in a good state of preservation, we need to go deep. So ExoMars can drill 2 meters into the subsurface. It's a big difference from 17 centimeters to 200 centimeters.
It's a huge difference, and Curiosity and Perseverance both have their own little drills going on. Famously, the InSight mole tried to get beneath the surface and kind of failed. So I'm wondering how the drill is designed differently to penetrate deeper than we've ever been able to before.
So you can think of the ExoMars drill as a mini oil platform. So you have one drill tool that is about 75 centimeters long. So with that, we can penetrate about 50 centimeters into the ground. You always need to leave a bit of room because when the fines come out of the borehole, the drill cuttings, they build a small cone under the drill box. And we don't want those fines to go into the drill mechanism. That means that we keep the box some 20 centimeters off from the surface. So that first drill tool is 75 centimeters long. And then we have 3 extension rods that we can screw. Each one of those is 50 centimeters long. And so if you assemble the entire drill string, then you reach the maximum depth of 2 meters. And we have, by the way, another thing that is interesting. We have an infrared spectrometer in the drill tool. So there is a small sapphire window, and so we can look at the borehole walls as we are drilling or as we are extracting the drill. The temperature during the day on Mars can go to a tropical 0 or 5 degrees C. But at night, it shoots down to minus 100 degrees C. So the subsurface behaves like a beautiful freezer. As long as you go deeper than 50 centimeters, the temperature is basically the average between night and day. So some minus 60 degrees. This is great for the preservation of organic molecules because it's like having them in the freezer in the lab. But when you collect that little sample and you take it out from the hole, you're bringing it out from minus 60 degrees to a much higher temperature. And so we wanted to take measurements in the natural or native conditions of the sample so that we could compare further readings that we would get inside the analytical laboratory with these ones to see if there was any change.
That's really clever. Are you only going to be taking spectra of the material down where the actual sample is being grabbed, or are you going to get a little bit of a rock record, essentially, as you're going down the drill hole?
Unfortunately, we cannot take spectral measurements precisely of the place where we collect the sample because the window of the spectrometer is 20 centimeters above the sample collection chamber. So if we wanted to take a reading of exactly the same place where we collect the sample, we would have to go and drill another hole close to where we collected the sample and take a reading. So for the time being, what we are doing is we are taking readings all the way down, but stopping 20 centimeters shy of the place where we will collect the sample. So infrared spectra we collect in 3 different places. So we have the panoramic cameras. They take images in the visual range. We have one high-resolution camera that is aligned with an infrared point spectrometer. So that we use to try to understand what is the general bulk mineralogy of outcrops and rocks that we will see on the surface. Then we have the infrared spectrometer on the drill, and then we have another, the highest performance infrared spectrometer inside the analytical laboratory. And that one actually guides the other instruments.
Well, there's so many instruments that are interacting here. And then what happens to the samples after they're actually procured is a whole other tale, right? So we'll get into a lot of these things. But I think it's so clever that you guys decided to take spectra on your way into this borehole. We've never gotten an understanding of what that material is like that far deep down into Mars. So who knows what we're going to learn even from that alone, let alone from the samples themselves.
Well, the reason why the payload clicks so well is because for this mission, we did something that we had never done before and we have never done since. When the proposals for the instruments arrived and we selected the ones that were best, we didn't choose what the payload would be from those proposals. Instead, we invited all the winning teams to 4 days of thinking what the payload should be. And they all sat together and they themselves negotiated who was going to do what and bring what. And the result was that we ended up combining several proposals to make new instruments that had not been originally proposed. And that's how we all ended up agreeing that basically the rover would be like one facility where everybody works together. So that over the years has cemented very well. So that's why we have, for example, each observation is nested on the previous one. So we are not presenting the results of instrument A and instrument B, but rather we are attacking the problem with everything and hopefully then presenting what we learned about a place or a sample.
We've seen people have issues in the past, say with InSight, they wanted to make sure that they weren't going to hit a rock And if they did, they were going to have to find a way to hammer that little instrument around it. Instead, in this case, you guys are using a ground penetrating radar. So what are you looking for underneath the surface that'll tell you that that's a good site for drilling?
This ground penetrating radar works at higher frequency than the one on Perseverance. So we penetrate not as deep, but we have better vertical resolution. And it is designed, of course, to learn about the subsurface, but also to guide the drilling operations. And the two things that we are most interested in doing is, one is mapping subsurface layering. We want to understand, for example, if we see an interesting outcrop with mineralogy that we could associate with the past presence of water, and we can analyze a sample from the surface, but we think that the real juicy science is going to be if we can access that very same formation 2 meters down. And so what we do with a GPR is we move the rover in a special type of pattern to create a three-dimensional map of how that outcrop manifests itself below the surface. And then we know how deep we have to go through regolith to penetrate the sedimentary layers we are interested in probing. The other thing that is very important for us is if there is a hard basalt boulder that would stop the drill, we don't want to go there. I didn't mention this, but it takes us between 4 and 5 days to drill 2 meters into the subsurface. So it's an important investment from the point of view of operational resources. The GPR is able to tell us where we have obstacles that are, let's say, bigger than a football.
If it takes so long to do a single drill hole, how many different locations are you hoping to drill?
So the nominal mission is in the order of 7 months. I should mention that a nominal mission is what you pay for. So when you go to industry and you say, hey, I'm going to place a contract with you for a rover, this is what you guys have to guarantee. You have to guarantee my nominal mission. And that means that they are obliged to test for 5 to 10 times that duration all the components, depending on whether it's motors or hinges or various other gizmos. But to some extent, the duration of the nominal mission drives the price. So the projects don't want to make it super long. On the other hand, you have to be able to show that you're going to accomplish your mission objectives within the nominal mission. So for ExoMars, it's 7 months. And so we had to figure out what it was that we would do during that nominal mission. And in essence, what we are trying to do is investigate between 5 and 6 different locations. And in each one of those locations, we want to be able to at least collect and analyze 1 surface sample and 1 subsurface sample, deeper than 1.5 meters. And in 2 places, so if we find something particularly juicy, we want at those locations to do vertical surveys, which means collecting and analyzing samples at 50 centimeter intervals. So at 0, 50, 100, 150, and 200 centimeters, to be able to tell how things change with depth.
I mean, if other past Mars rovers have been any indication, perhaps this is going to last a lot longer than we expect. So that's a good amount to get back, even just from a nominal mission. But fingers crossed, we'll get even more as, maybe it goes into its extended mission, maybe.
Let's hope. So what I'll say is that our nominal mission was very optimistic. I mean, I don't think we're going to be able to do all that in 7 months. If there is any debugging to be done for things that may not be super peachy, or even just the first few weeks and couple of months where you learn how to become more efficient at operating the rover. That means we're going to go slower than what we predicted for the nominal mission. But we don't mind because we use that to buy ourselves elbow room operationally. And that means that we have consumables to be able to go much, much longer. There are more ovens than what we expect to be able to use during the first 7 months. And so, as you say, if there is a possibility for an extended mission, we are well prepared for it.
Well, we've explored a few different locations on Mars, not to this depth, but we have rovers in other locations, Gale Crater and Jezero Crater. But this one is going to be landing in Oxia Planum. And I understand it was like a 6-year-long selection process to figure out this location. Mm-hmm. So what makes this such a compelling place for a potentially life-detecting mission?
When we started the landing site selection process, there were the engineering constraints because you need to land safely, otherwise you get no science. But for the scientific requirements, if I could summarize it in a way that is simple, we said all other things being equal, we want to go as far back in time as possible. And we said we don't want anything that is younger than 4 billion years. And to give you an idea, Gale is on average, because of course you have rocks of all kinds of ages, but it's about 3.6 billion, and Jezero is about 3.8. We didn't know where Perseverance was going to go when we did the landing site selection process or where we started it, but we knew, and we have learned a lot from curiosity. And we wanted to go as far into the Noachian as possible, because we knew that was the time when there was more water on Mars. Then, because our entry is parabolic, as was that of the MER rovers, your landing ellipse is very long and thin. So it's something like 90 kilometers in length by 8 or 9 kilometers in width, which means that we needed a place where there was water, because we thought that would have been super important for life, or the life that we are hoping to detect if we get lucky. But it had to be present more or less anywhere in the landing ellipse. So we needed rocks that would be representative of a large body of water. And that's what we ended up going for. And that's one of the major hypotheses for the landing site. It's where one of the largest river systems on Mars, Kogum Valleys, ends. And between Oxia and the North Pole, there is nothing that would have acted as a barrier for water. So the hypothesis is that this could have been a coastal area for perhaps a large northern ocean. And the reason why we think Oxia was submerged at the time when the clays formed is there is a delta in the southeastern part of the landing ellipse that is 100 million years younger than the clays we're landing on. And for that delta to have formed, it means that the sediments that were brought by the river have to have experienced a sudden stop when the river went into a larger body of water. And then they precipitated and formed the delta formations that we see today. There is a very nice paper that has come out last month that basically shows that the clays in Oxia and the clays in Mart valleys are connected. There's almost 300 kilometers between the two places. So basically, the phyllosilicates, the clays in Oxia, are not just a local expression, but rather a sign of a much larger thing that was happening, that was at least regional, and perhaps may have been, well, if not global, but a large area of Mars that involved this finely laminated place where the laminations are the rings on a tree trunk. Each one of them basically records an instant of deposition and wetting that happened 4 billion years ago. So it's a very interesting puzzle to try to put together.
That really is. And the fact that we have this location combined with the other locations that we've been on Mars is going to give us a much better picture, because even in recent months, we were talking about the complex organic molecules that Curiosity has found in Gale Crater. I was just speaking with one of the team members about how much I would love to know whether or not those similar kinds of organics are located somewhere else, whether or not that was just a localized phenomenon or if they're all over Mars. And especially at an earlier point in Mars's history, it's going to be really interesting to be able to compare all these things together.
Indeed. But studying organic molecules on Mars is complicated because we know there are cosmic organics that get delivered all the time. And those have nothing to do with life. They are basically the result of random reactions that happen in deep space. We have recently gotten the OSIRIS-REx samples from the Bennu asteroid, and they have been fantastic and so rich in organic molecules. So we can expect that some of that material may have been delivered to Mars over the many billion years. So if you like, looking for signs of life, it's a bit of a Sherlock Holmes endeavor, because you have to be able to disentangle what may have been the contribution from microorganisms that may have existed so many million years ago from this other cosmic signature. And if you think that some of those biosignatures, if there was life, also had to go through 4 billion years of exposure to the elements, then it's going to be an interesting nut to crack.
And I think that's what's so interesting about particularly the MoMA instrument you have on board, the Mars Organic Molecule Analyzer. You're not just like trying to figure out whether or not there's complex organic chemistry, but you're doing something even deeper, trying to understand the chirality of the molecules themselves. And for people who are kind of unfamiliar with this concept, can you just briefly explain what chirality is?
Sure. There are some organic molecules that are very important for life, like, for example, amino acids, which are the building block of proteins, and sugars, which we need, that if you make them in the lab, you get 50% of the left-handed configuration and 50% of the right-handed configuration. This means that if you assemble these molecules, whether it's in the lab or in deep space, you expect to have equal amounts of the two possible configurations, the two-handedness. But life doesn't work like that at all. Life assembles the molecules it needs from basic ingredients, and so it only makes what it requires. And in the case of terrestrial life, it turns out that we are built from left-handed amino acids and right-handed sugars, with some exceptions, but for the most part, it's like that. So if you look for traces of life on Earth, you find that the amino acids are left-handed. And it is only when they start to degrade after things have died and the cells, the membranes rupture and all that they had in the cytoplasm gets spilled into the geologic record, that as they degrade, these molecules racemize. So they become again 50-50. So if you were to land on Mars and you look for organic molecules and you do detect this chiral excess, then that's a very, very important clue that you may have hit the jackpot. And in the past, we were not so sure, because when you look at meteorites on Earth, whether you collect them in Antarctica or in the Moroccan desert, some of them we know come from Mars, others from other bodies. In some cases, we could detect a bit of enantiomeric excess, so a bit more of one handedness than the other. And so we were a bit concerned with that. But OSIRIS-REx and Hayabusa, which got measurements from organics obtained from the asteroids, those are racemic. They are exactly 50-50. And this is great because it's telling us that those excesses we were seeing on meteorites on Earth probably had to do with terrestrial contamination. I mean, there's so much life on Earth that it's very, very easy to get a bit of that into the samples we want to study. So indeed, chirality is a very, very important biosignature. And as you mentioned, on the MoMA instrument, when we use the gas chromatograph part of the instrument, we have 4 columns, and one of them is a chiral column that will allow us to tell if some of the organic molecules have a chiral excess.
We'll be right back with the rest of my interview with Jorge Vago after this short break.
Hi, I'm Kirby Runyon, planetary geologist at the Planetary Science Institute and founder of Planetary Experience Consulting. Think of your favorite photograph from the moon or Mars. Have you ever wanted to read the stories recorded in those rocks? You can learn how. This October, I'm co-leading a 3-day expedition to some of New Mexico's finest planetary geology analog sites, and I'd love for you to join me. From October 15th through 19th, we'll explore tube-fed lava flows at Carrizozo, soak in the volcanic desolation of Kilbourne Hole Volcanic Crater, and stand at sunset over the sublime White Sands National Park. These are some of the same landscapes where Apollo and Artemis astronauts have trained. We'll also visit Spaceport America, the New Mexico Museum of Space History, and the Las Cruces Challenger Learning Center. Space is limited to just 20 people, and for every person who registers, the Planetary Society will receive a donation. Head to planetary.org/travel to learn more and save your spot. I hope to see you there.
It's so exciting, not just for the potential of telling us more about whether or not life did exist on the past there, but also there's a clue there, which is that if it's the same chirality as we expect here on Earth, that tells us something. And if it's different, that tells us a whole other thing, right? So this is like a really deep way to probe the history of life on another world, if we can find signatures of that. And if we don't, that's also very interesting.
Yeah. So when Phoenix landed in 2008, we had the first wet chemistry lab, and they were trying to look for organic molecules and having a tough time. When they started analyzing in the wet chemistry lab the samples they collected from the surface, for the first time, they detected the presence of perchlorates. And perchlorates are these exotic oxidants that don't exist in many places on Earth because you need a lot of UV light and a source of chlorinated molecules in order to produce perchlorates. And they're very easily washed by liquid water. But when Phoenix found perchlorates, initially they were considered to be a curiosity. But then curiosity also detected chlorinated molecules. And in between, people went and looked at the results of the Viking landers and remembered that they had found chloromethane and dichloromethane on the Viking landers. And slowly, people pieced together what was happening. And that is that these perchlorates are pervasive on Mars. Because there is not much of an atmosphere to speak of, the UV light reaching Mars is much stronger than the one reaching our planet. And so this UV photochemistry is able to produce oxidants that we don't find very often on Earth. And among those are these perchlorate salts. And what happens is that all the missions that we have sent to Mars to look for organic molecules so far have used the same method, which is you get a bit of Mars sample in an oven, you heat the oven, and you desorb the organic molecules and then study them. But what happens is that these perchlorates, which are normally inert, as soon as you heat perchlorates above 150 degrees, they dissociate and liberate the 4 oxygens they have, which then are free to go monkey around and oxidize anything they find. And so most of the organic molecules, they will turn into CO2. But then the chlorine that is left behind says, I also want to combine with somebody. And so looks for, what is the simplest organic I can find? Methane. So it will latch onto methane and produce these chlorinated organics, which were found by the Viking landers and were also seen by Curiosity. So one thing that we learned from Curiosity that we want to find a solution for is what to do if you know ahead of time that you're going to have perchlorates mixed in with your sample. So in MoMA, we have 32 ovens, and those do the analysis as was done in previous missions by using pyrolysis, that is, by using heat or high temperature to desorb organics. But to work around the perchlorate problem, for the first time, we are bringing what is called laser desorption mass spectrometry. So we have this UV laser that fires trains of pulses, and this does very soft ionization of the sample and is able to extract the organics without actually perturbing or doing anything to the perchlorates. And this works particularly well for the bigger organic molecules, which are the ones that are more diagnostic, because it's only life that can make relatively complicated organic molecules.
Still very startling how complex a lot of these organics are, even just on, Ryugu and Bennu as an example. So getting even more complicated things out of Mars is just absolutely amazing. But first we have to get there, which is a whole journey, right? And you said that you've been working on this since, 2002. It's been a long journey to get there, but we finally have a potential launch vehicle. Can you talk a little bit about what that launch is going to look like when it finally happens?
Sure. I should explain this because people are used to having missions to Mars take about 9 months to get there. And ours is going to take longer. And I would like to explain why. So if we would take the normal trajectory, we would arrive during the winter time. So this is not very good for a rover that uses solar panels to gather its energy. So what we're going to go do instead is we're going to launch, but instead of going directly to Mars, we're going 1.5 times around the sun. So the first launch trajectory, the one in September, launches, goes to the orbit of Mars, but Mars is not there. So we just keep on going around the sun one more time, and then we get to the orbit of Mars again. Mars is waiting for us to land. The second window is cleverer. So what it does is we launch and we go to Mars, and Mars is there waiting for us, but we don't land. We do a gravity swing. We come out of the ecliptic much faster, and then we go around the sun again and we land at the right time of the year. And that's why we gain those months.
Wow, that is like a long journey, but I mean, it makes sense. Are we not waiting for a different time of year or a different year itself to launch just because of launch timing and windows, essentially?
Well, it turns out that if we were to wait the next 26 months, the opportunity is much less attractive. So this is the better one to use. And if we do that 1.5 times what is called a T3 trajectory, because that number It's how many half revolutions you do around the sun. So the fast one is a T1, and this one that is a bit delayed is a T3. If we use this T3 trajectory in 2028, then that puts us on the surface in mid-spring. So we have the rest of spring and all of summer to have our mission on.
Mm-hmm. Oh, this is going to be so exciting to get there, but it's, 2028 by the time this thing finally launches. And the mission has gone through a significant evolution in terms of its launch and landing plans. You've had to redesign quite a lot. So where does the mission currently stand in readiness for its actual launch?
So at the moment, we are working together with SpaceX, because we're launching on a Falcon Heavy, to do what is called the spacecraft composite environmental test. Basically is, once you have your spacecraft elements ready, you want to make sure that they will meet the launch environment in terms of vibrations and also in terms of the sound-induced vibrations, which is something people perhaps don't know about. Is not only the vibration that you get from the engines and through the landing structure, but the actual screaming of the rocket as it launches produces so much pressure in the air that also is a cause of concern that you have to test.
There's so much you have to test in order to actually get into space. I love all the videos of shaking spacecraft to make sure they don't shatter themselves apart. But there's also the planetary protection concern in this case, because this is a biology-seeking mission, essentially. How do you make sure that the pieces of this spacecraft are sterilized enough, especially on these long timescales as you're building it, so that we don't accidentally detect Earth life while we're on Mars?
It was handled in two different ways. So the spacecraft itself, the parts that will not touch the samples and do not concern themselves with the search for life, those are dry heat sterilized to kill any bugs, and they're assembled in a clean room under pretty clean conditions. So normally, a normal clean room is an ISO 7 class. And here we have, inside the clean room, we have a special tent where conditions are even cleaner and where people have to dress as astronauts, more or less, to go in, where we actually build the spacecraft, the rover. But the actual parts that concern themselves with the sample, those were put through a much more rigorous building process. We have what is called a glove box train. And these are chambers where you cannot get in, but you actually have these special gloves that you put your hands through so you can work with the things inside. But in this case, it had 4 stages. So each means that every stage was cleaner and more stringent than the previous one. So every single nut, bolt, piece had to be dry heat sterilized, labeled, and put through that glove box train. And it basically took 6 months for anything to go from the clean to the super clean to the ultra clean until we get to a place where the analytical laboratory was assembled. It took 1.5 years to go through the process and build it up. And then once it was done and it was taken out, the analytical laboratory is divided in 2 parts. The lower deck has what is called the ultra clean zone, and that is pressurized. It's 100 millibars above ambient pressure and is periodically purged with ultra clean argon. And we take plugs from the atmosphere to make sure that it stays ultra clean. And in the upper layer of the analytical laboratory are the instruments that look into the ultra clean zone through windows to make sure that they don't break the cleanliness. With the exception of MoMA. MoMA is the only one that has to be connected to the actual gas volume inside. So the inlet is kept sealed and it will only be opened on Mars. And as I mentioned, roughly every month, we take a plug of gas and we look at what's in there to make sure that it stays clean. Having said that it's ultra clean, it doesn't mean there are no organic molecules. There are some organic molecules because, for example, the gas chromatograph columns of the MoMA instrument, they themselves have organic molecules in what is called the solid phase, and they degrade, so we can see those molecules, but we know where they come from. They're from the instrument itself. So I just want to clarify that when I say that something is ultra clean, it doesn't mean that there is absolutely no organic molecules in the background. The trick is you make it as clean as you humanly can, and then you have that organic background well characterized so that once we land on Mars and we open the analytical laboratory, we can check what it is we have there before we actually start the search for, what Mars may have on hold for us.
It's such a complex process, but if you do it right, it gives you the opportunity to basically get into one of the deepest questions humanity has ever asked, right? Are we alone in the universe? Did life exist on another world in our solar system? It's some fundamental science that could completely change the way we see ourselves in the context of the universe. So it's worth going through all these steps, even if it's wildly complicated and a labor of love to make sure it's all sterilized. But for you personally, if we did find some indication from this rover that there might have been life on Mars, and we can't just do that with a single mission, but if we did find some clue to that, what would it mean to you personally?
Well, it would be the happy conclusion to many, many years of work, not just from me, but from the 300 plus scientists that have been for so long working and trying to put this mission together. And as you say, very often people ask me, so what are the chances that you're going to find life? And over the years, I've tried to break it down in probabilities. And I say, I think that if everything works well and we land safely and the rover works as we hope it will, I think there's 100% chance that we're going to find organic molecules because, Curiosity found them and other missions have found them. I think because the subsurface has such great promise for the preservation of organic molecules, I give it at perhaps 50% that we may find something that is perhaps suggestive, but that we will be able to prove that there was life at the landing site. I give that, perhaps at 10%. I think that to be sure, we will need to bring back samples and have the chance to study them on Earth because we can do so much more in a lab on Earth than what we can do even with the best missions that we can try to put together and work remotely. Robotic missions are amazing, but they do have some limitations. I'm a strong believer also on bringing samples back, as we did from Ryugu, and you see the amazing results that we have gotten from those.
Fingers crossed someday. We're all hoping for that, right? Because if the ultimate goal is not only to understand whether or not Mars had life, but also maybe potentially send humans there, we're going to need some samples back first, not just to understand the perchlorates, because those are deadly for humans, but to understand everything else that's just sitting there on Mars waiting for us to discover. So this is one next step in that journey, and I'm so excited to see what this rover discovers. Thank you so much, Jorge.
Thank you so much for having me here.
The Rosalind Franklin rover won't be able to talk to Earth on its own. It has no direct communications link back to home. Instead, it relies on a spacecraft that's already been quietly orbiting Mars for nearly a decade. the ExoMars Trace Gas Orbiter, which launched back in March of 2016. The orbiter is going to serve as the rover's lifeline, relaying the data back to Earth once it lands. But it's also been doing amazing science while it's been in orbit around Mars. Here's Dr. Bruce Betts, our chief scientist, to tell us more. Hey, Bruce.
Hey, Sarah.
Talking about a new rover on Mars soon. That's so exciting. What? No, we've been waiting for this rover for so long, and I remember being so excited about it back when the ExoMars program got started. And this is something that we didn't actually get a chance to talk about.
In the 19th century?
Well, I mean, yeah. Oh, man, that my millennial heart breaks every time I hear that one. But
that was the 20th century.
God, long ago. But we didn't actually get a chance to talk about it when we were having the conversation about this big missing piece, which is the Trace Gas Orbiter, the ExoMars orbiter that's already at Mars, which I wish I'd brought up in the conversation.
Yeah, the Rosalind Franklin rover needs a way to communicate its data back to Earth, and it does so by communicating probably primarily with the Trace Gas Orbiter, and then that relays the information. So this is something that NASA's done with their landers and rovers for a long time. And in fact, I believe the radio systems on the Trace Gas Orbiter and on the Rosalind Franklin rover are provided by NASA. They're the Electra radio communications package. Basically, you get much higher data rates because the orbiter is comparatively close, and then it can use its bigger antenna and also communicate with Earth over time. Mostly orbiters are in polar or near polar orbits, and usually you get a couple passes per day, but I believe that's what they've got planned with Trace Gas Orbiter. And it'll only be 14 years old in orbit or something, which, hey, they've got the European Space Agency's Mars Express has been there since 2003, still working, and Mars Odyssey, the NASA's Mars Odyssey, since 2001.
Yeah, so I think what's really cool about this is not just that it's in place and is going to be relaying all this information back from the orbiter, but it's actually been doing science for all those years that it's been waiting for its rover friend. So what has it taught us so far about the Martian atmosphere?
Its primary mission is science.
Science!
Looking for trace gases, which sounds unimportant, but turns out to be very scientifically important. Most notably looking for methane, which is on Earth. Most of the methane put into the atmosphere is from critters, a technical term for life. And so there were reports and have been reports of finding methane in the Mars atmosphere, both ground-based and at Mars, but kind of near the edge of the data being a lot of noise compared to the signal, and also transient, which would be more interesting because it's either geology that's active or life that's active. But TGO has not seen any methane, I believe, since I last heard, and so it's kind of a difference, and it was specifically designed to look for that, so I tend to believe it offhand. And they also have been doing other stuff, so they study other atmospheric things. They've done some surface work. They've got a neutron detector that detects hydrogen in the upper meter or so of the surface, which can be from water ice, and so is intriguing. And so it's a good thing to remember that there's all sorts of science going on at Mars and all sorts of spacecraft in orbit as well as on the surface that are doing great stuff.
And now the Trace Gas Orbiter will someday soon, and I say soon, as in, 4 years from now, we'll finally have a friend.
Yeah, and that's going to be exciting. Looking forward to the rover.
Oh yeah, man. I mean, I want to know how all of those organic detection experiments go and how they compare to what Curiosity and Perseverance have been finding. Because if we can compare across all these different places of Mars, there's so much that we can learn. But again, I'm going to have to be patient. It's the thing about planetary science. It's like I want so badly to see these things happen. I just have to be patient, Sarah.
Yes, happens on very long time frames, but then they come and go, and you're like, wow, that was a lot of years. What happened?
I mean, this is why I end up anthropomorphizing these things, and I know you hate it, but I just get so attached. I love their adventures.
No, that's great. Your enthusiasm is one for the ages. Let us go on to Random Space. Rewind.
Kind of sounds like you were yawning your way through that.
Oh, I'm excited. I love this one because it's so out there. On Pluto. Let's go back to Pluto and hang with me. And there's a lot of approximation here. A lot of so approximately on Pluto, an average, it's just a funny concept. An average weight woman would weigh about the same as an average weight newborn baby on Earth.
Dude. That's a cool comparison, but also makes me feel like you could sneeze and fly away. I wonder how far I could jump. We should, Space Olympics on Pluto. That would be sweet.
Yeah. All the ices, you could have different events, cross-country carbon dioxide ice skiing and downhill methane. It'd be wild.
That'd be cool.
All right. Here's looking forward to Rosalind Franklin and wishing best wishes to all the rovers that are there. Everybody go out there, look up the night sky, and think about happy roving dogs and cats and rovers. Roof. Thank you and good night.
We've reached the end of this week's episode of Planetary Radio, but we'll be back next week with more space science and exploration. If you love the show, you can get Planetary Radio t-shirts at planetary.org/shop, along with lots of other cool spacey merchandise. Help others discover the passion, beauty, and joy of space science and exploration by leaving a review or a rating on platforms like Apple Podcasts and Spotify. Your feedback not only brightens our day, but helps other curious minds find their place in space through Planetary Radio. You can also send us your space thoughts, questions, and poetry at our email, planetaryradio@planetary.org. Or, if you're a Planetary Society member, leave a comment in the Planetary Radio space in our member community app. Planetary Radio is produced by the Planetary Society in Pasadena, California, and is made possible by our members from all over the world. You can join us as we work to support the search for life and the exploration of other worlds at planetary.org/join. Mark Hilverda and Ray Paoletta are our associate producers. Casey Dreyer is the host of our Space Policy Edition, and Matt Kaplan hosts our monthly Book Club Edition. Andrew Lucas is our audio editor. Josh Doyle composed our theme, which is arranged and performed by Peter Schlosser. My name is Sarah El-Ahmed, the host and producer of Planetary Radio. And until next week, Ad Astra.